Okay. So, previously, well, a couple episodes ago, because I made an episode talking about some random nonsense, we figured out a way that if we had a pre-sheaf on our space, we could produce then a sheaf via sheafification. Right. Well, it's a little bit more than just being able to turn pre-sheaves into sheaves. In fact, we know that the collection of pre-sheaves itself forms a category. And I claim that this process of sheafification actually defines a functor, right? So we know what it does on objects. I claim that so we need to construct what it does on maps, and then of course, check that it respects composability of maps and whatnot. Well, I'm just going to tell you how to define a what it does on maps. So, suppose we had a morphism of sheaves. And I need to tell you what it's going to do as a morphism. What is going to be the induced map on the sheafifications, right? Well, that means I need to give you the data of a bunch of maps for each U for the sections over U. And of course, maybe I should write F plus. Of course, you need to check that this is actually a morphism of sheaves, the compatibility maps. But if we think about it, so S being in F plus U, remember that means that S is a literal function from here into the product over all the stalks, such that, and we had this other defining condition that said, for all points Q in U, there existed some open set sandwiched between Q and U, where and some section of F over that open set, where for all of the points in the open set, the stalk at T was simply given by the value of the function. Remember, S. Specifically, we also demand that whatever S's value is at some point of U is that it lands in that stalk, right? So S at P has to be in F sub P. Right. So that was the defining condition. So what do I need to do, right? I'm trying to come up with a map. So suppose we had some S here, and I need to tell you where F plus sub U is going to send S. Where is it going to send S? Well, it's got to send it to some function on U, but now because it's going to be in the sheafification of G, it's got to be in this product of stalks over G, right? So something that I don't remember if I articulated before. Well, maybe one other thing to mention is that given some morphism of pre-sheaves, I get an induced map on the stalks. So for every point, I get an induced map on the stalks. What is that map? Well, it's just sort of the obvious guess, I would say. So let's think about what this map has to be, right? So the elements of this are equivalence classes of a pair of an open set in some section, right? So suppose I have an open set containing P and some T, which is this, right? So the equivalence class of this pair is called the germ, right? And I basically need to tell you where this equivalence class is going to go. But first, let me just define it on a pair. And then the claim is, it doesn't depend on representatives for this equivalence class. So where should I have this send, well, okay, so where should the equivalence class of this pair, where should I have f sub p send this? Well, remember again, f is a morphism of pre-sheaves, so I get a map over every open set. So U is still going to be an open set of my space containing P. But now F sub U of T, right? This is some pair. My F sub U sub T, because this is a morphism of sheaves, that's going to be in the sections of G over U, right? So I'm gonna send it to this equivalence class. Okay, so now I'll leave it to you to prove that that is actually well defined. By the way, I may as well mention this now because I'm going to use this later in the video, or maybe the next video. I might break this up. This is a long video I had planned. Proposition. Oh Lord, I don't remember what it is, but this is from Hartshorn. Probably misspelled it. In the chapter 2, section 1. On sheaves is that the original morphism is an isomorphism if and only if for all points in your space this induced map is an isomorphism. So we're going to make use of that in a moment, but also let me say this. Let me give you a warning. Warning. This does not say that if f sub p is abstractly isomorphic to g sub p for all x in your space, then these sheaves are isomorphic, right? So that it does not say that, right? It says specifically you need to start with some, globally defined pre-sheaf morphism, and then if the induced map on all of the stalks is an isomorphism, then your original thing was an isomorphism. Okay. So I got a little sidetracked here, but let's go all the way back. So now that we know that we have an induced map of stalks, let's return to the thing we were trying to do. Gosh, this whiteboard is a mess already. But we were trying to define a map between the sheafifications, right? And so we started with some S, which was a particular map from U to this product of stalks. And I wanted to produce from that some S from U to the product of all the stalks of G. So what should I do? Well, remember that this thing here has to be a function, right? So it's enough for me to tell you what it does to define it for all points in U. So I'm going to define this to do what? Well, first I'm going to take Sx, right? So we know that Sx lands in the stalk of F at X. And now I also have this induced morphism on the stalks, right? And so I can apply that F sub X. And now that is going to be a thing that does in fact land in G sub X, right? Okay, so by the way, remember that we generally care about, sheaves of abelian groups or something like that. So you'll want to convince yourself that these induced morphisms on the stalks also respect those group operations or vector space operations, what have you. So that at least we've defined, okay, we've managed to define this map on every level. Well, almost. One should formally verify that that this property holds, right? But now in place of this F, you want to put a G. So that I'm also going to leave to the reader. Okay, don't at me too much. I mean, of course, if you all really want in the comment sections, you know, if you ask me nicely, maybe I'll show you the actual proof. But I'm gonna get into some, you know, gritty details soon enough. So okay. So where are we now? So we have, right, we've constructed not only do we have a method of taking pre-sheaves over to sheaves, right? So this is the process of sheafification. But remember that every sheaf is a pre-sheaf, right? It's just a pre-sheaf plus some extra conditions. And every morphism of a sheaf was just a morphism of the underlying pre-sheaf. So in fact, there's a way to go back, right? And pretty trivially, we have what we generally call a forgetful functor. So we can also go from the category of sheaves back to the category of pre-sheaves by just forgetting the fact that it satisfies the last two conditions. Now, in general, right, we already know it seems like these two categories aren't quite the same, right? So we've got this pair of maps, and you might wonder if they're like inverses to each other. I mean, we have seen the example of you know, continuous bounded functions being a pre-sheaf that isn't a sheaf. And then sheafifying that gives us the continuous functions. So one would think, well, then there's two different pre-sheaves, right? Because the pre-sheaf of continuous functions is also the you know, that sheafification. So you know, are these categories quite the same? So by the way, we have in general for two categories. What does it mean for categories to be the same, right? Well, just like how in a category we define an isomorphism to be, you know, a pair of mutually inverse maps, and isomorphism of categories says that if you compose either of these maps, you should get the identity right on the nose, right? And that makes sense because, I mean, that's just how we, you know, isomorphisms are usually defined. But so that's step one. But there's a little bit of that's almost too strong for our purposes, right? Because normally in categories, or oh, I don't want to say in categories, but you know, oftentimes in mathematics, it's we only care about things up to isomorphism, right? So for example, if you thought about the category of all finite dimensional vector spaces over the real numbers, right? So that's a category. Well, actually, there's there's a whole set theory worth of vector spaces, right? Because you could take, you know, just the zero-dimensional vector spaces already. You could just take like any set with one element and turn it into a vector space. But of course, we know finite dimensional vector spaces, you know, if you're n-dimensional, then you're isomorphic to Rn. Right. So somehow, so this is like a huge category. It's like bigger than ZFC or something. And yet each like isomorphism class of each object, well, we should be careful. I'm, you know, somehow inserting choice here, but each isomorphism class of each object is just, you know, represented by Rn for some natural number n, including 0. So sometimes, if I started with some object in C, right? And if I applied F to that object, and then I applied G to that, I don't really need it to be exactly equal to X again. It's good enough for it to be isomorphic, right? Should be good enough for it to be isomorphic. But that's not maybe quite enough, though, right? Because what I really have here, right? So this is a functor, and this is a functor, right? So I could have equalities of functors, but remember, we have another way of comparing functors, and that is the idea of a natural transformation, right? So the correct way to sort of lax this condition is to say that this is an isomorphism. So it's a little bit stronger than just saying for all objects, these are isomorphic. What I really want is I want there to be natural transformations between these functors and the identity functor. So these should be natural transformations. So of course, that would imply this result about the isomorphisms on the level of objects, but it's a little bit stronger, right? So weaker than this condition, stronger than this condition, right? Okay, so that's a little bit of abstract nonsense. By the way, we're going to get into some real abstract nonsense in a couple episodes. But what's the point? So we might ask, okay, these two functors, right? These two functors, probably not going to be bang on equalities, right? When we compose them with each other. Is it possible that they're isomorphic, right? If I compose the forgetful functor with sheafification or the other way around, right? Another way to say this in more down-to-earth terms, let's say, is, if I started with a pre-sheaf and I sheafified it, right? Then remember that there's this idea, like if there's some sort of order to the world, if I started with a pre-sheaf and sheafified it, then certainly if there's in the case when F was a pre-sheaf, or sorry, when F was a sheaf to begin with, it should be isomorphic, right? Sheafification shouldn't do anything up to isomorphism, right? So one way to say this is to ask about, well, say I started with F and then I sheafified and then I forgot. I applied the forgetful functor, right? And I look back at the underlying pre-sheaf. That in general should have something to do with F, right? So in order to really compare F, because a priori I don't know what F is, well, how do we compare objects? Well, I should have some sort of morphism, right? There should be some sort of map. So let's try and come up with a map that compares F to the forgetful functor, right? So that would be like in this picture over here. Well, if this was an isomorphism, right? If these arrows are isomorphisms, they can go either way, rather. So this would be considering a map from the identity on the category of pre-sheaves into the composition of the forgetful functor and sheafification, right? So let's just try and come up with a map. And by the way, we're going to see this sort of pattern pop up in a very general sense soon enough. Okay. Take a quick breather while I double check my notes about where I'm going. So, well, maybe, you know what, I'll leave it here. That was enough blabbing. And in the next video, um we can dive more into the nitty-gritty details. So I'll see you there soon, I hope, if I can find where to stop recording.